So we go to the second part, which is the hazard maps, considering the GCM data. So under these sessions, we will go more on detail about the general circulation model, GCMs, and their scenario, and then applying the GCM output to the flood hazard maps. So what GCMs, general circulation models? Okay, basically we cannot carry out the laboratory experiment for this purpose. Okay, we cannot quantify the climate change. We cannot conduct the experiment to look the pattern of climate change in the lab, because you can see the Earth system is too complex to be simulated in the reactor. That's why GCM we call as a general circulation model. Some others people will say GCM stand for the global climate model. So basically it's the same terms. So this GCM actually is a computer-based version of the Earth system and used mathematically to simulate the climate system and the interactive between the system component. So the GCM actually able to simulate the present and also project the future climate with foreseen or unforeseen by greenhouse gases and aerations. So that's about the GCM. It's a mathematical simulation that simulated by the computer, and basically the pattern and trend of the climate change able to being addressed by using the GCMs. As I mentioned before, you can see on this diagram, this is one part of the GCM. If you able to cut the GCM and able to represent in terms of the figures, okay, it's something like this. You can see there is an ocean, and then there is an atmosphere, and then as you can see there is a clouds, and then the process at the atmosphere we have the evaporation, the rainfall, everything actually have been modeled in the GCMs. So if we want to know what happened in the future, for example, if we put some greenhouse gas to the model, so for example 100 years, what will happen? So that thing have been tested and simulated in the GCM. So this is another framework of the GCMs. So you can see all the process to represent the global, to represent the process of the, basically we call as a process at the atmosphere, everything, okay, have been represented by the, able to represent in the GCMs. So there is a lot of the GCMs. Okay, as you can see, the first table is the GCMs for the first version of the AR assessment reports, and then the table 2 actually is the most recent from the AR6. So each model actually have been produced by different country. Okay, so for example, for the Canada, okay, you can see this table 2. Canada, they produced the CAN ESM5. Okay, and then for the Japan, they produce their own GCM MRI ESM20. Okay, and etc. So there is many GCMs are available. So each GCM actually have their own strength. Okay, of course, each country claim their GCM is better, But in term, if you want to study the climate, normally we select several of the GCMs, and then we do some we call as you take their assembles. That means you have 2 or 3, probably a lot lah, 5, 6 of the GCMs, and then you run analysis, and then you assemble their value. That means you find the average value from all the GCMs. So why we doing like that? Because we want to reduce the uncertainty. Okay, if you take a one GCM only, probably their GCM cannot represent the current scenarios. So we don't want that thing big occur. Okay, because if you have a bias or error or differences in the current scenarios, if you project, for example, for 100 years, okay, the uncertainty or the bias will become more large. So to overcome to that problem, when we want to simulate, we try to using several GCMs to reduce this uncertainty analysis. So that's about the GCMs. And then when we talk about the GCMs, we call as we have this another term, which is climate scenarios. Okay, so as you can see, the climate scenarios is a plausible indication of what the future could be like over the decades or century, given a specific set of assumptions. So this assumption including future trends in energy demands, emission of greenhouse gases, changes in the use land, and as well about the behavior of the climate system over long time scales. So climate scenarios is the assumption of what the future climates. For example, okay, we have observed, okay, for example, 1916 until 2022. So this one is observed. And then in future, okay, for example, until 2100. So you have an assumptions, the sets, what happened in the future. Okay, probably the carbon dioxide emission will be higher. Okay, we don't know. And then probably CO2 will be lower in the future. So we have several set of the climate scenario to project in the future. So that's about the climate scenarios. Climate scenarios actually have been defined in the assessment report that produced by the IPCC. So the most popular one we call as the special report on emission scenario. This one from the AR4. So in the AR4 assessment report 4, they have categorized the climate scenarios based on the A1, A2, B2, B1, and then there is between A2 and B1 they have A1B. So this data set, they have categorized the climate scenarios based on the emissions. So for example, for the A1, you can see the future world of very rapid economic growth, global population that peaked in the mid-century and declined thereafter, and rapid introduce of new and more efficient technology. That's the definition of the A1, which is in the future, okay, there is a rapid growth, but they're able to tackle the problem related to the these emissions. They're able to control the emissions. And then we have the A2 climate scenarios, or we call as a series A2, which is a very heterogeneous world with continuous increase of global population and regional-oriented economic growth that more fragments and slow than in other storylines. That means the A2, okay, we have a growth population of human, but in terms of the pollutant, we can see there is no some sort of way or some sort of the effort to reduce the pollutant. So we can call series A2, okay, for the future, the world more polluted, okay. And then we have the series B1, which is the pollutant have been increased, but the world there is a motion to reduce the greenhouse emissions. So that means the world during that time is more clean, and then all countries try to reduce the greenhouse, because we can call the series B1 the world more green. So that's why you have this graph, and as you can see for the emissions of greenhouse gases, we can see there is an increasing of the series A2 and the decreasing for the series B1. That's about the series. And then for the AR5, they introduce new definition, which is RCP, which is Representative Concentration Pathway, RCP. So as you can see, they basically it's the same definition like the series, but they have changed the term based on the carbon dioxide pollutant, the concentrations, which you can see at the left side. So you can see for the red line, we call as RCP 8.5. You can see there is a unchecked pollution. That means during in the future, okay, until 2010, the pollutant or the emission of the carbon dioxide, okay, will be increased. That means there is no motion from the country to reduce the carbon dioxide emissions. There is an increase of the trend for the RCP 8.5. And then for the RCP 2.5, this one 2.5, the green line, so that's mean there is an extreme carbon dioxide cut down. That means all country try to together to reduce the greenhouse gases. So that's the between. This is show how the RCP have been developed. And then nowadays there is a new climate scenarios based on the AR6, we call as a shared socio-economic pathway. So for this one, actually basically it's the same, but I do not want to touch more, because basically for this new one, I do not study yet. Okay, because if you go through on my background, last time I have studied and I have produced several papers related with series and also RCP. But nowadays, okay, since there is a new AR reports, so they have to introduce a new data set of the climate scenarios. So this one, I think, is more they try to look on the social parts, not like before this. For the RCP, they look more on the concentration of the carbon dioxide. But this new climate scenarios, they look on the social, they look on the together with the carbon dioxide concentration. So it's much comprehensive. Okay, finish about the GCM and climate scenarios. So the next step after we know about the GCM, so we want to try to use the GCM for the another applications. For example, in our case, we try to use the GCM output to flood hazard maps. So for the information, you guys, GCM, as I mentioned before, is designed for the global. Okay, it able to represent the whole planets. But in terms of if you want to focus on the small region, for example, if you want to study the hydrological or hydraulics, okay, we cannot use the GCM directly, okay, because as I mentioned before, their scale is very large. So that's why there is some adjustment that are need to convert the GCM from the large scale to the small scale. And this adjustment, or we call it as a bias correlation, we call it as a downscaling methods. Okay, penurun skala dalam bahasa Melayu lah. So when you able to downscale the GCM, so you can use for others application. Okay, in our term for the flood hazard maps. So you can see on this graph, okay, GCM, you need to downscale until RCM, and lastly to the SDS for the small scale. So there is a lot of methods and techniques to downscale, but basically we can categorize these downscaling methods into two. First is statistical downscaling. The second is a dynamic downscaling. So for the statistical downscaling, normally it's very straightforward to use, and most of the time we as a individual, we can use this method to downscale the GCM by our own. Okay, a lot of software, a lot of the methods can be used. Okay, for me, I apply the statistical downscaling, okay, that being published by the Wilby. That's the very powerful tools to downscale the GCM. And then for the downscaling, the another technique for downscaling we call as the dynamical downscaling. So the dynamical downscaling, normally we as a individual, we cannot do this method, because to run the dynamical downscaling you need to have a very powerful computer, or we call as a computer. It's very expensive and quite big, and normally the agency like have a lot of money, they can buy the supercomputer. And most of the time for the dynamical downscaling, okay, in Malaysia, normally this one have been run by the Jabatan Meteorologi Malaysia. Okay, they're able to produce and run the dynamical downscaling. I think precise. And then Nahrim, okay, Nahrim also have the able to downscale the dynamical. And then I think some institution like the UKM under Prof Tanggang, so he also works on these methods. So there is advantage and disadvantage using these two methods, and as you can see, the advantage and disadvantage have been shown on the slide. So if you're interested to know about the downscaling, okay, you guys can read more. I also using several downscaling method to downscale the GCM. Okay, normally for me as an individual, normally we run statistical downscaling techniques, which is more cheap and easy, and then even though we using low spec of the laptop, we still able to manage the results. Last time I using the statistical downscaling model SDSM. This one quite popular. SDSM is very, I think it's quite uh, uh, difficult to run this software because you need to take time to learn. But once you have been master, it's quite easy to produce the climate change model. And then we have another model which is last WG. So last WG, I think, is quite very straightforward software, and I think most of time, if you ask me as a personal, okay, I will recommend you to learn last WG to start. If you want to start using, if you guys want to start to downscale the GCM. Okay, the main reason is very simple and very straightforward. But the limitation of the last WG is, okay, because the last WG they using the database of the climate scenarios and GCM, they it being stored in the last WG. So if you want to using the current GCMs with the current climate scenarios, for example, nowadays we have the climate scenarios from the AR6, you cannot using it. You cannot run by the last WG because the latest of last WG they just contain the climate scenarios based on the RCP published by the AR5. So if you want to run for the new climate scenarios, okay, we need to using, for example, like the SDSM or another techniques. Okay, so that's the two popular software to downscaling. So if you want to read more, okay, you can read the publication of me, which is the application of the SDSM and last WG for simulating and downscaling of rainfall and temperature. So that's about the methods. So what the variables that obtain from the downscaling GCM output? So the first thing, the most important variables that we want to downscale, of course, we want to rainfall. Okay, the second one is a temperature. That means you need to know the maximum and also the minimum temperature. Besides that, if you want to look the solar radiation, humidity, wind velocity, and other meteorological data, okay, you can downscale directly from the GCMs. But most of the research, most of studies, we like to focus these two variables, which is rainfall, okay, because rainfall is related with the floods, related with the droughts. That's why these variables is the most important variables. Besides that, people like to study the temperature, okay, because temperature also related with the drought, related with the water supply. So for the long term, normally temperature is quite crucial to be used in the analysis. That's why these two parameters being widely downscaled from the GCMs. So this is the example of the framework on how we utilize the GCM outputs. Okay, so this framework I take from my master, I think, from my master. So you can see I have GCM, and this GCM, I select a series A2. So this one is a climate scenario. And then the second step, I using a downscaling technique to downscale GCM. For what? For future, the current and also the future of the rainfall and also the temperature. And then I using the hydrological modeling to simulate the stream flow. So this framework, at the end, I will obtain the future stream flow or stream flow that being disturbed by the climate scenarios. For example, the discharge, for example, for 100 years. Okay, and then we have several set of climate scenarios. For my study, I just focus for the A2, one scenarios. But now this, you can focus for many climate scenarios is much better. So because we want to know in the future how the projection of the climates, how the projection of the discharge is look like. So that's how we utilize the GCMs. After that, after you get the stream flow, okay, you can do anything the related that need the stream flow as their input. For example, you can extend this framework to the hydrodynamic like Mach 11, okay, to get the water level or flood, and then you can do the hazard map due to the climate scenarios. Okay, so this is the another framework if you want to use for the flood hazard maps. So basically, I think after this, you guys will go through on how to using the HMS and also the HECRAS. Okay, I think on the following sessions. So during that times, you guys will get an idea on how to using the rainfall to simulate the discharge, and then from the discharge, for example, you need to convert to water level, and then barulah you boleh tengok this flood hazard map. Okay, basically the input data, which is rainfall, so that's rainfall data we need to manipulate with the climate change. Okay, we have this RCP 8.5, RCP 2.5. Okay, we have this type of the rainfall series, and then this rainfall series you insert and apply in the hydrological and also the hydrodynamic modeling to get the flood hazard map. So this is the example how the flood risk map accordingly to the RCP. So RCP, okay, jangan confuse, RCP is a climate change factor or climate change scenarios. So from this map, you know which area or region or the sub-catchment will facing a high of will have a high risk of the flood occurs. Okay, for example, this one, the red line. So when you know there is a high risk of the floods, so you need to able to tackle the problem. So that's the advantage when on how we want to integrate the climate change in the flood risk map.